Hi, linear algebra students. So in this video, I'll be proving the row pivot theorem. So let's state and explain the theorem. Okay, so if A is m by n, notice my color code. Actually, I should have talked about this in the class, but the m here is going to play an important role. Remember that these are the rows. Then the four following statements are equivalent. Ax equals b is consistent for every vector in Rm. Okay. Each vector in Rm is a linear combination of the columns of A. The columns of A span Rm. And finally, A has a pivot in every row. So I should tell you right away that D is the most important statement because it's the one that is the easiest to verify. You just have a matrix, you row reduce it. Do you have a pivot in every row? Yes, the first three statements are true. No, the first three statements are false. That's the way this theorem works. Okay? And I will shorten the proof just by telling you how we can easily establish that A, B, and C are equivalent. That's what I wrote over here. So A is equivalent to B just by the definition of matrix vector multiplication. The multiplication of A with X is actually the linear combination of the column of A with weights x1 to xn. So saying that Ax equals B is consistent for every B really means that every B is a linear combination. So there's a solution to this equation equals B. Okay? So for example, if I put the equals B here, you see the connection right away. If Ax is equal to B, if this is consistent, then automatically this is consistent. So there will be a linear combination producing B. Okay, now B is equivalent to C by the definition of what's a span. The span is the set of all linear combination of the columns of A. Okay, so I will actually just read this and comment a little bit because it's easy to get confused. So okay, this is a set, this is a set, this is a set of vectors, this is a set of vectors. So the span of the columns of A are the linear combination of vectors, so that are the columns of A. And since A has m rows, these vectors have m components. So the linear combination of vectors of m component is certainly inside Rm. So this set is contained in this set. Okay, this is clear. This is actually obvious. What's a little bit less obvious, and this is what B, this is why we need B, is that if every element of Rm, if every vector of Rm is a linear combination of the columns of A, then by definition, each element of Rm is inside the set of linear combinations, so inside the span, and therefore Rm is contained in the span of the columns of A. And remember that when two sets are contained in each other, they're actually equal. So that's why it's obvious that B and C are equivalent. Okay, so the hard part in this proof is to prove that A or any other statement, but we'll choose A, is to prove that A is equivalent to D. Okay, so now what remains is to prove that these two are equivalent so that everything will be tied up together. And the way we will accomplish this is by proving that if D is true, it forces A to be true, and if D is false, it forces A to be false. Hence what I wrote over here. So we have to prove that they are either both true or both false. And for that reason, the proof will have these two steps. We will first suppose that D is true and prove that A is true. And after that, we will suppose that D is false and use that to prove that A has to be false. So now I'm erasing everything here, and I will just keep the theorem, and that will be it. So step one. So we suppose that suppose D is true. That D is true. Okay, this is actually, I would say, the easy part of this of this proof, because it really means that there is no row that could possibly make the system inconsistent, because what makes a system inconsistent is a row full of zero with a pivot in the constant column. Okay, so this means that there is no pivot in constant column. And the reason for that is because they are all in A. In A. And basically, this is because the coefficient matrix A and the augmented matrix AB have as many rows, right? They have the same number of rows. So have the same number of rows. Okay, so it means that this forces A to be true. So AX equals B is consistent regardless of B, just because there cannot be a pivot in the column of constant. And of course, as a result, it means that A is true. Okay, so we finished. So, okay, we proved that if D is true, A is true. But that doesn't tell anything about if D is false. Like, if D is false, if we don't prove, if we just end here and don't prove anything else, A could be true or false when D is false. So we need to actually prove that if D is false, A is forced to be false as well. So this is the next step of the proof. Okay? Okay. So now, okay, step number 2. So suppose that D is false. D is false. Okay. So this means that the RREF of A, which is unique, has a row of 0, because if the coefficient matrix doesn't have any row of 0, it has a pivot by definition, because the pivot is the leading entry. Okay, so then it means that the RREF EF, let's give it a name, okay? We will call it U. So we call it U. Has a row of zeros. Okay, this is really by the Gaussian elimination. It's by the definition of what is RREF. Okay, and it means that for every B in Rm, the system AX equals B is equivalent to some system UX equals D. Okay, so so AX equals B is equivalent to UX equals D for some D. So we don't know what is that vector, like in Rm, it actually depends on B, but we know that there is a vector D for which these two systems are equivalent. So now what we're going to do is we're going to construct a vector D that makes the second system inconsistent. Okay, so consider a vector D that has a entry of 1 exactly where at the row of 0. Okay, so having an entry of 1 or a component of 1, let's say, where U has a row of 0. Then in this case, it means that the system Ux equals D is inconsistent. So Ux, actually, yeah, I'll write underneath. So it means that Ux equals D is inconsistent. Okay? And then, basically, by equivalence, it means that the first system is inconsistent because you could actually perform the row operation in the reverse direction and go back to your inconsistent system AX equals B. Okay? So by equivalence, AX equals B. Or actually, let's just say that the vector D obtained by like backward reduction, let's put it this way, the vector D, or the vector B, sorry, B obtained by, and now I have to unfortunately erase the first couple of steps here. By performing the reverse EROs from U to A, on the vector D, will make AX equals B inconsistent. Okay? So what it means basically, even if we cannot necessarily find it in its full generality, it means that if A doesn't have a pivot in every row, we are able to construct a vector D that makes the system Ux equals D inconsistent and come back to the matrix A in order to find a vector B that makes the system AX equals B inconsistent. So basically what we prove is that there is a vector B. There is a vector B for which AX equals B is inconsistent. And as a result, A is false. And this is the end of the proof. Just so that you don't get confused, I will actually erase, or actually, no, I'll just say this is the end, okay? So this is it. This is the proof of the row pivot theorem. So I just remind you, these are easily seen to be equivalent, and we have to prove that if D is true, A is true, and if D is false, A is false. And that's what we have done from beginning to end. So I hope this video was helpful. See you in the next video.